Did everyone have a wonderful outside and a sunshine and a lunch? Okay, well, you're back here to see another wonderful talk. We are talking about, what are we talking about? Multi-strategies for...
Multi-tenancy strategies with Django and Postgres.
You seem to know what you're talking about. I'll let you take it away.
Good afternoon, Django Noughts. So the focus of my talk today is going to be, we have decided to use Django and Postgres on our website. What can we do to ensure that data doesn't leak from one user to another user? And in particular, what can we do about developer mistakes so that developers don't make it possible for users to leak data between systems? Now, I'm going to be talking a lot about tenants and tenancies in this talk. If you're not aware of a tenancy or a tenant, the idea is it's an isolated set of data that is using shared infrastructure. So a really good example of that would be Gmail, where you might have millions of users that are all using Google's computers. They're all stored on the same servers. But I, as a Gmail user, should not be able to see the data from another Gmail user in the system. I have my own mailbox, and those things should be kept completely separate. In most situations, a tenant will correspond directly with the user, but that's not always going to be the case. If you think about something like Salesforce, a company will have an account on Salesforce, and they might have 100 users that are attached to that company. Within that company, those 100 users can all see data relating to those customers, but they shouldn't be able to see data from a different company that is also using the Salesforce platform. So I'm going to talk about 3 major strategies today. I'm going to spend most of the time on the last one because I think that's probably the most interesting. And my assumptions here are that you are Python developers who've used Django, and in particular have used the Django ORM before. If you've never used the Django ORM, but you have used Postgres or SQL databases of some sort, you'll probably get about 70%, but there will be some that may go over your head. There's also many setup variations on these, like little tweaks you can make. I'm just going to be covering the broad outlines here. Hopefully by the end you'll have picked up 1 or 2 new strategies. So the first major strategy is that every tenant in your system gets their own app server and gets their own database on completely separate domains. In a sense, every single tenant has a complete new copy of your system. This is great for code simplicity. It's very difficult for devs to accidentally make a mistake and expose data from a different tenant. And in fact, it's quite difficult for them to do that. It's great for data isolation, and not just data isolation, but also performance isolation. If you have one particular tenant who is hammering the database a lot, that's not going to affect any of the other tenants because they're all using completely separate database servers. And depending on your cost model, it also makes it possible to pass through the costs of hosting directly to a tenant. If you have some big corporates and you say, well, we're going to give this system to you, but you're also going to pay for the hosting costs associated with your tenancy, then it's possible to do that. Where it becomes painful is when you have lots of different tenants in the system. Every time you bring a new tenant on, it means you have to stand up new app servers, you have to stand up new databases. You can automate that process, but every time you add moving parts to a system, there's something that's going to go wrong. And let's say, for example, you create a new AWS server. Well, what happens if something goes wrong in that? And it actually takes 40 minutes rather than the expected 3 minutes. Then you have a support call. There's lots of things that can go wrong. It's also not possible to easily run cross-tenancy queries. If, as a software developer, I want to know how many users are across all of the tenants in the system, I have to query every single one of those databases one at a time, bring it back to Python, and then aggregate the data together. From an administration perspective, it's also a bit of a pain. When I want to take backups, I have to back up every single database one at a time. And when I want to push out new migrations, I can't just push it out to one server. I have to push out my new Django migrations to each server one at a time, or in parallel, but you still have to do it many times. So usually this is a bad idea. Why do I mention it all? In some circumstances, it can actually be a good idea. For example, if you have a very small number of tenants. I had a client once who had a custom written CRM that was written just for them. There was no assumption of any tenancy information whatsoever. It was one company using that one system. They decided they wanted to license it to another company. Well, we could have spent months going back through the system and saying, okay, every single thing now needs to have an account ID attached to it. Or what we end up doing, we spent a couple of days standing up a new database server, a new application server, and we were done with it. It's also sometimes the only option if you have corporates with an IT department that has particularly strict security policies. The next option is where we have a single Django app server backed by multiple databases. The idea here is that we have custom middleware that looks at the incoming requests, decides which tenancy is this particular request relating to, and then in your custom Django database router, you go back and you look at the middleware and say, well, what tenancy are we currently dealing with? Okay, we'll route that now through to the correct database. The nice thing about this is that hooks to do it are already there in Django. You have to write a bit of code, but you're not messing around with any deep internals or anything. This inherits almost all of the advantages and the disadvantages of having multiple app servers, but you do save on app server hosting costs. And while the code is generally simple, there are a few gotchas. So, for example, Django transactions by default only apply to the default database, which may not be the database they're actually working with. And you think everything's working fine until you discover that, hang on, the data's inconsistent here because transactions weren't being applied to the correct database at the time. The biggest problem it has, though, is what are you going to do with the situation where you push out a new update, which includes migrations, and you start migrating each of those databases one at a time, and you've got 3,000 databases to do, and on database 1,500, something fails, and you realize there's a problem with your migrations. There's no rollback here. Now you have a single set of app server code that's somehow having to deal with 1,500 databases on the old migration schema and 1,500 databases in the new schema. That's going to be a bit of a pain to deal with. A nicer variation of that is to use a schema per tenant. Now, if you're not familiar with Postgres schemas, think of them as Postgres equivalent of namespaces. Within a Postgres database, you have many little smaller databases that we call schemas instead. Those schemas are all completely independent of each other, and in fact the table definitions inside each schema could be different. Now, we probably don't want to do that. It's theoretically possible. Instead, we want to have the same database definitions across all of the schemas, but instead inside each schema is just the data for one particular tenant. And again, the idea here is that middleware will look at the incoming request, and on the current Django database connection, it will set the current schema to use. Again, the majority of your code can simply pretend that tenancies do not exist. The middleware has already taken care of it for you. And unlike the last setup, because all of your because all of your schemas sit within the one database, transactions work as you would expect. Transactions cover across schemas. It's a bit better for very large numbers of schemas. You can dump the database as a whole, sort of. The big problem here is that when you use some standard Postgres tools, pgdump, you'll quickly discover that Postgres has some internal limits on the number of table locks that can be taken at once. Now that can be increased by changing the Postgres settings, but you're forever going to be chasing your tail if you have to increase this and increase this and increase this. Every time you do that, you're setting aside fixed memory buffers to deal with that. And cross-tenancy queries are now possible. Because your data all sits in the one database, you can actually query multiple schemas at once. It's a bit ugly because what you effectively do is select from this tenancy, union this tenancy, union this one, union this one, union this one, and if you've got 10,000 tenants, that's a really, really big query you're going to be running. And the administration deployment situation is a little better. However, again, as I mentioned, there are transaction limits. When you try and run your migrations, you think, okay, I'll put everything in one big transaction and I'll run the migrations across all of my schemas until you get halfway through and then Postgres says, oh, I've run out of transaction locks. So I've run out of table locks for your transaction. If you try and do this without transaction at all, then we're back to the previous problem where you could get halfway through, half your schemas have been updated, half your schemas haven't been updated. If you've not used it before, connection pooling is a way of sharing database connections between multiple requests. So normally, in the simplest configuration, you have a request come in, Django creates a connection to the database. When the request is finished processing, it tears down that connection. That creating connections and tearing down connections, that has overhead that can add up over times. So the idea behind connection pooling is you generally have a proxy sitting between your application and the actual Postgres database, and it will hold those connections open forever so that the Postgres overhead of starting and stopping connections doesn't exist. Depending on your connection pooling setup, it's also possible to share connections between requests concurrently. It's not a common setup, but it is a possible setup. Because we are setting the current schema on the connection, our connections are now stateful. If you try and intersperse requests to the database from multiple requests simultaneously, they're going to clobber each other and you'll end up using the wrong schema. There is a third-party package called Django Tenants, which basically does all of this for you. All of the middleware for routing towards schemas. It looks at the subdomain and says, well, based on the subdomain, this is the schema you want to use. The fact that there's third-party code to do this is quite nice. It also has the ability to run your migrations in parallel. So rather than upgrading each schema one at a time, it'll parallelize them and do 30 at a time. Probably the most interesting setup, though, and the one that you've probably used before and most developers would use intuitively, is where you have a single app server, you have a single database, you have a single set of tables, and you share those tables between the different tenants. Within each table, you record who does this particular piece of data belong to. Now, in order to keep the data separate between the tenants, there's a bunch of strategies that we can follow. So these are the three things that we're going to be looking at today, and the nice thing about these three is they're somewhat independent of each other, and you can adopt them incrementally. So if you had an existing system, you can actually add these onto an existing system and get a bit more security. There's some common characteristics that they all have. Firstly, the code is not as simple as the previous methods. You always have to bear in the back of your mind that there are multiple tenants in the database, and while these things can help avoid make mistakes, it's still possible to make mistakes and accidentally expose data. The isolation is okay, but it's not great. Again, coding mistakes can have a problem. However, if you have thousands of tenants, then it's basically the only option you're going to have. Cross-tenancy queries are possible. In fact, the problem is accidentally doing cross-tenancy queries. And the administration and deployment situation is fine. Everything sits within the one database. The standard Django workflows that you would follow apply here. So here's an example database diagram for a task tracking system. And down the bottom is some associated model code. The idea here is that we're going to have custom model managers and query sets which have a standardized interface on every single model in the system that says, limit the data that I'm selecting out of this table to just one particular tenant. Now, one of the nice consequences of standardizing on one thing across all of the tables in your system is that if you're using class-based views, the class-based view doesn't need to know what model it's dealing with. It can always call filter tenant, and the code will just work. So you can have your base classes which apply this tenancy filtering automatically, and for most of the system, it just comes out for free. If a table doesn't join directly to your table, to the account table, which is the tenant table in this particular example, then we just use standard ORM joins in order to get back to that table. Now, as a practical matter, the middleware has a copy of the request, and from that request it's able to figure out which tenant we're supposed to be dealing with, or maybe it looks at the user in the request and from that figures out which tenant we're supposed to be dealing with. And since the view has access to the request, it now has access to the tenant ID. But not everything else in the system is going to have the tenant ID. And now we could pass that tenant ID down the system, down the call chains, but that's going to get really painful really quickly. Just as a pragmatic thing, you probably want to store the current tenant ID in the middleware so that you don't have to pass it everywhere through the system, and keep track of that in thread local storage. Now, if you've not used it before, thread local storage is essentially global data that only applies to the current thread. So if you're running on a multi-threaded server, you won't clobber data that relates to the wrong thread. The reason we want to do this is that, if you're not aware, Django only creates one copy of each middleware object on startup. So you can't store the data in the middleware object itself, or it will get clobbered by whatever the next request that happens to be simultaneously processed is. So there are some caveats about this. Whoops, wrong direction. Number one, if you write custom SQL, you're on your own. there's no help. You need to make sure that you don't make mistakes with any custom ORM code, any custom SQL code. Having the joins automatically applied to every single table can actually change the meaning of some of your aggregate queries. It's not a common circumstance, but you will run into it when you write your queries and say, why is the data not coming back how I expected it to? Which means that sometimes you will need to bypass and not call filter tenant and in fact apply the tenant filtering manually, even though you are using the ORM. A more subtle problem is that by default, if I have a model with a foreign key that refers to another model, that second model also creates a reverse foreign key in Django back to the original model. Now what this means is that if I have a shared table, so for example I have a list of countries, I don't need to duplicate that between all the tenants because the list of countries is fixed, and I have users who all have a country, then by following user.country.user_set, that user_set is the reverse foreign key that Django creates automatically. I'm not just accessing users that relate to that country for the tenant that I started with, I'm accessing users from the entire system that relate to that country. So you need to be careful about that. If you want to be strict, then what you can do is turn off the reverse foreign keys. You need to do that on a foreign key by foreign key basis or use a base class that does that by default. And again, if you want to be strict, there's a system of checks called Django system checks. If you've not used those before, go look up the manual, they're fantastic. They're code that will run on every Django server startup. What you can do is introspect all of the apps in the system, get the models for those apps, look at the fields in each of those models and make sure that every single foreign key field has had the reverse foreign key disabled. That way you can't accidentally escape out of it. But the biggest problem of all is that the developer could simply forget to call filter tenant, and nothing's going to stop them from doing that. So, whoops, what can we do about that? What we can do is we can remember in each query set where the filter tenant was actually called, and if it wasn't called, then we will log a warning or raise an exception when the query set actually goes to fetch data back from the database. Or you do something else like in debug, you log a warning, but in production and on CI, you actually throw a hard error so that it can't escape. It's a bit nicer if you're doing refactoring because it can be a real pain sometimes when you have to constantly stop and start. If you do this though, you'll quickly run into the difference between Django's base manager and its default manager. If you've ever used soft deletes in Django, you'll have run into the same situation before. The default manager in Django is the manager that you normally use. Django also has the notion of a base manager, which is, you can think of that as the master manager that has access to everything in the system. Django uses this for things like refresh from DB, if you want to get the data back from a record. It uses it for migrations, it uses it for fetching foreign key relationships, and you need to provide a way for Django to fetch data from the database without having called this, because Django's not going to call this. Call filter tenant, I mean. Now, normally when we design a database, we like to normalize everything. So if we have a look at our task management system again, each of those tables has a reference to another table, but only project and user have a reference back to the account, that is the tenant table. If we needed to filter a subtask according to the current account, we'd join the subtask to task, join task to project, join project to account, and then check that we're using the correct account. What we can also do is denormalize that. We can copy the tenant ID into every single table in the system. Why would we want to do that? Well, firstly, it simplifies our code. There's no joins that we have to do anymore in order to filter by tenant, which means those aggregate query problems that I was talking about before no longer apply. And it's also desirable for row-level security, which we'll talk about next. It doesn't meaningfully affect anything else. There may be a performance impact, but that performance impact could be positive or could be negative depending on the ratio of writes to reads in the system. It's harder to move data between tenants. No longer are we just updating. So let's assume, for example, we wanted to merge two accounts. No longer are we taking all the projects for one account and pointing those to the new merged account. Instead, we have to do the projects and the sub-projects and the tasks. Sorry, the projects and the tasks and the subtasks. There's a lot more records that we're going to have to update. There's the potential to introduce errors here. let's say we forgot to do a transaction and we're doing that merge and we got halfway through, then now we have data that's half changed and data that's half not changed, and some of those foreign keys are not going to be consistent with the other data that's in the system. So it's possible for coding mistakes to introduce problems, and you have your standard denormalization caveats. Your database will be bigger because of duplicated data. In particular, your indexes, you're going to have a lot more indexes in the system. That means that every time that you update an account record, every single record in the system that has an index associated with it that points to the account is potentially also going to have to be rewritten by Postgres, which means no longer is Postgres just going to have to update the projects that relate to an account for their indexes. It's also going to have to update the tasks and the subtasks. There's a third-party package called Django Multi-tenant, which assumes that you have already denormalized your data, and it automatically adds where clauses onto every ORM query that you do, so that it assumes, well, the tenant ID is already in here. Rather than you having to manually add the where clauses, I'll just do it for you. It also provides a replacement foreign key class that avoids the problem I spoke about before about escaping from your current tenancy via the foreign keys. And also worth mentioning, the reason for the existence of that project is that the company behind it, Citus, they make a Postgres extension which will automatically look at the tenant ID and use that to shard your data between multiple servers. So from your perspective, it looks like a single Postgres server, but in fact, it could have 20 or 30 servers behind it, and your software doesn't have to change at all. Even better, Microsoft bought that company, and now it's like a couple of clicks in Azure when you set up a new database to get that. You also pay a lot more because you're paying for many more servers, which is why Microsoft want you to do that. And finally, Postgres row-level security. So Postgres has the ability to add security checks on a row-by-row basis. Now that's not just selects, that's also updates and inserts and deletes, and it will validate that every time you run a query against a table, that some check, the check being the SQL code that you define, that condition is met. Now that check itself could do selects. You probably don't want to do that because it's really easy to blow up the number of queries that you're going to do in your system and have major performance issues. So you probably want to keep it to a relatively simple expression. If you look at row-level security tutorials on the internet, you'll see that almost all of them use Postgres users. That's probably something that I think is a bad idea. The problem with Postgres users is that they're not specific to a database. They're global across all databases on a Postgres server, which means if you have your database and someone else has another database that's using the same server, and you're both creating and deleting users, there's a really good chance you're going to be clobbering each other and you're going to end up having a bad time. And that assumes you even have permission to create users. If you have sysadmins that are managing your databases, they're probably not going to give you those permissions. They're going to say, no, we gave you a user, use that one. So what we can do instead is that, again, middleware, there's a common theme running through this here, we can have some middleware set the current tenant ID on the connection, and then in the row-level security checks, we can look at what the current tenant ID is and make sure that that matches the data that's we're operating against. Now, in the example here, we've set this variable called Django.accountID, and note that the dot in that name is very important. What we're actually doing here is we're abusing Postgres settings. Postgres thinks that we're trying to set a configuration item for a Postgres extension called Django that we just happen not to have loaded yet, and it says, well, that's fine, you can temporarily override that configuration setting. And later on, we then pull that back out again and use that for our row-level check. Because it's a configuration option, it's always going to be a string, which is why we have that cast from int there. Now, there are some caveats for Postgres row-level security. Again, because we're setting some state on the connection, you need to make sure that you're not interleaving requests simultaneously across the same connection. There are potential performance impacts. If you run an explain analyze on your query after activating row-level security, you'll see all of these extra row-level security checks that have basically been tacked onto your queries by Postgres. Most of the time that should be okay as long as you were already filtering by the tenant ID in your Django code. But if you weren't, then the row level checks are now going to add these extra filters which may not have indexes associated with them, and now you may have performance problems. So you'll need to just keep an eye on things once you've activated it to make sure that there's no unexpected effects, and if there are, you may need to look at the indexes that you need to apply. And again, the Postgres query optimizer is pretty good, but the more complicated the query is, the more chance that it's going to choose a query plan that's not the one that you expected it to use, and you may have to jigger around your queries a bit in order to get it to operate performantly. If you're doing your local development in Postgres, you probably just have one user. That user is actually a super user. That user will completely bypass any row level checks. So your row level checks will appear not to work at all. You need to make sure that when you are doing your development and when you get to production, that you didn't accidentally connect to the database with a super user. And conversely, when you're taking your backups from the database, you need to make sure that you are using a super user. If you were just using PG dump and that was not a super user, and that user had row level security checks applied and was not seeing all of the data, you will not get all of your data in your backup, and you'll have a very bad day when you go to restore from backups. So, in summary, multiple app servers and databases, very simple to code, but can be costly and painful with a large number of tenants. Using a single app server with multiple databases and multiple schemas, the big problem you're going to have here is partially applied migrations. Django managers, they're very nice at detecting missing filters, and they can provide consistency to your code. Denormalizing tenancy data can simplify your code at the expense of database size. And Postgres row-level security checks are a really nice fail-safe. In case you forgot something in Django, the database is there, got you back, just to make sure that you don't accidentally mess up something. And I have code samples for most of these. It's pinned in my repository, so if you'd like to have a look at some of these things with a proof of concept, then feel free. Questions or comments?
Who has questions?
Or comments?
Thanks for running through all those. There's a lot of things to keep in mind, and a lot of places you could accidentally trip over your own feet and accidentally show the world things that aren't meant to be seen. Are there any ways that you can systematically avoid those problems, or give any confidence that you haven't hit those problems, or is this just a matter of you need to make sure you've got test coverage and things?
Yeah,
like
test coverage. The thing that I found, we actually used mandatory filtering on a project once, and I had so much pushback from developers who say, "Oh, it's constantly complaining that I forgot to filter," and I'd ask them, "Well, should you be filtering?" Yes. It is like the Nazi checker of making sure that you've put filtering in, but I've actually, personally, I like it the most as something that forces you to consider, should I be filtering this or not? And you always have the escape hatch. You can use all objects, but it also means it's really easy to audit your code and say, find me all of the instances of all objects, because I know that those ones aren't going to have filters applied, and I can go and double check those.
Oh, we have more questions. I'm getting my steps in.
My last name's Russell, so we can make this work. Watching this talk, I saw myself, we went through this process at work a couple of years ago, and all the things you talked about were all the things that we dealt with. So I'll ask a highly specific question. Using thread local storage to store the context, the tenant context, I've always felt kind of uneasy about that, partially because of globals, but partially because as a local developer, I don't trust my knowledge of threads and whatever else. Are there common pitfalls that someone like me should be looking out for, or edge cases that I might not have considered?
I'm not sure of any common pitfalls specifically. I would just say test, and make sure you test multiple requests simultaneously. I actually had some test cases that would just do tests over and over and over and over again in two different threads. It's kind of a pain, and it's non-deterministic unless you have pauses and sleeps that you insert just to make sure that, but even that assumes that you put the pause and the sleep in the correct location. On thread local storage, though, I can say Django uses it internally. I was a bit wary of it at first and was like, well, Django's doing it, so if, I don't know, Django async doesn't work with it, well then so there's a bunch of other core Django code that's going to break. So that, I don't know if that makes you feel better about using it.
A little bit.
For the recording, that was a little bit. Sadly, we are out of time, so let's thank our speaker again for the great talk.